Hey, what's up, guys? Yeah, so today I want to talk about the interesting computational complexity class called the Polynomial Hierarchy. Okay, so to be honest, the first time I heard of this is why it makes me interesting in this computational complexity subject. Okay, because this is very interesting. Like, it's like when you start in the mathematical analysis, then you heard about the open set and the closed set. So let's maybe use another analogies that somebody give you G, which is a set of open set, and F, right? And in a real analysis, that you can define a set called G delta, which is all set, which is you can construct by the intersection of open set, and you can also construct F sigma, and you can also compute define a so-called G delta sigma, which is the intersection, the set of the intersection of the open set union with the union of such kind of set, and you can just keep going, define F sigma delta, and keep going. Okay, and the Borel, the collection of everything is called Borel set, and the mathematicians spend a lot of time just to prove that actually these all of them are different set. Okay, so polynomial hierarchy is also same. So in this video that I will standard, we will introduce a P and also standard NP and co-NP. This is, I assume that everyone knows this, and one can construct so-called sigma 2 and pi 2, also sigma 3 to the pi 3. So you can construct a lot of complexity class, which keep going, and finally total called PH, polynomial hierarchy. Okay. So let me just quickly, so this video just give you a definition and describe a little bit example. Okay, so remember let's remember L. So let's recall it. If L belongs to NP, means there is a polynomial verifier V, and there's a polynomial P such that if X belongs to L, then it is the Y, which is length of which the length is, let's say there is this Y belongs to 0, 1, and the length is, let's say, P of X, a polynomial of X, such that Vxy is 1. Okay, so V is a polynomial verifier, which you verify. For example, somebody give you a set, and then you ask, there is a satisfiable assignment, then you just do this. Okay. And also you can do the negation. So if X do not belongs to L, that means that for all Y for every certificate, such that Vxy is 0. Okay, so in order to do this, I only need to define this sentence, and then just do the negation, I guess, second sentence. Okay, so this is L belongs to NP. Okay. And then one can also define L belongs to co-NP, right? So let's say L belongs to co-NP, means that the X belongs to L, means that you change to for all Y, which is belong to 0, 1 to the P of X, such that the V of Xy is 1. Okay. So it means that if X belongs to this co-NP language, means that for all 0, 1 P of X, you can find there is such that the V of Xy equals to 1. Okay. Okay, so this is the definition of this. This is the definition of co-NP. Okay. Okay, so but there's there's some question which is not looks outside of it. Okay, and it's very natural. Okay, the first one is this IND set. Okay, so this is somebody give you a graph G and a K, and you want to ask that graph G has independent set greater or equal to K, of independent set size of greater or equal to K. Okay, and also there is a problem called exact in the IND set, which is all the G and the K, such that the largest. So let me just write the largest independent set has size k. Okay, and okay, so obviously what? Okay, so obviously that it seems like that this independent set is somehow like in this one is exactly in NP, right? So obviously that if you want to make a certificate, you just find a set, find the independent size of k. Okay, so your goal in this independent IND set, you just find a particular certificate which is size k, and then you just check whether it's independent. But this exact independent set is much difficult, right? Because if I find certificates and maybe it's not the same, right? It's not the largest one. Okay. Okay, and so this question looks weird. Okay, and also another question also looks weird. It's called a minimum set. Minimum circuit. So it's like you encode every circuit C, and the C is the smallest circuit. Compute C. Okay. So this means what? So this means that this exactly means that for every, so let me just write it. Okay. So this means that there do not exist another circuit C prime such that the C prime is exactly the same as C for all inputs, but the number of the C prime, because C is the smallest, right? So number of C prime less than the number of C. Okay, so this is called a minimum circuit. Obviously, the minimum circuit also looks weird. It looks like it's not in NP, it's not in co-NP. So somehow like we need a larger class to larger complexity class, natural class to accommodate this kind of question. Okay. Okay. So let me just introduce this sigma 2. Okay. So let's consider this class sigma 2. Okay. So sigma 2 is defined to be this. So let me just define this sigma 2 definition. So sigma 2. Okay. So sigma 2 means that the set of all language. Let me just write down word set of language x belongs to L if only if there is this U belongs to 0 and 1. The length is Q of X. Okay, for all V belongs to 0, 1. Length is also Q of X. This is not important. Actually, you can choose these to be different polynomials. You're just padding with zeros. Okay, and there is a polynomial Turing machine, deterministic Turing machine. Let's call it M, such that MXUV MXUV is 1. Okay, and also one can define pi 2. This is definition of sigma 2, and one can define also pi 2, just do a negation. So it's, let's say x belongs to L, and then change the exist to for all. So for all U belongs to 0, 1 with the length polysides, the exist V belongs 0, 1 to the polysides, the MX UV is 1. Okay, so what the hell is going on, right? Who cares these two complexity class? Okay, so fact that one can easily see that the previously what is exact independent set, so IND set is in sigma 2. Okay, why? So remember, let me just, so exactly it means that the largest independent size is exactly k. Okay, so let's translate into language. So I can write it as there is this S, and for every S prime, set S is an independent set. So it's independent set of size k, and S prime is not independent set of size k plus 1 greater or equal to k plus 1. Okay, so you see this independent set is asked whether your independent set is exactly k. This is the same as there is S, and for every S prime, set S is an independent set of size K, right? That means somebody give you already defined certificates. And for every S prime, which is larger with size larger equal to K minus 1, is not an independent set. So in order to prove this, in order to find this exact independent, you need two quantifier. One is for exist, one is for all. Okay, and exist in the beginning and the for all in the next. Okay, and obviously that is minimal circuit is in pi 2. Okay, because you can see that this is for all, right? For all and exist, right? So this means that not exist such that this. Okay, so let me just write this as language. So this means that this means what? So I can write this as this for every circuit C prime with size C prime less than size C, there is this X such that the C prime of X do not the same as C of X. Okay, so this is exactly the same as for all and exist. Okay, so you can see this is for all and exist. For all and exist. Okay, so if we see that for all and exist, so this is a natural language in pi 2. Okay, so this give us more powerful computational complexity class, and also tell you that why this sigma and pi are interesting. Okay. Okay, so once we have done this, and also there's a simple check that pi 2 is actually the code of sigma 2. Okay, so let me just recall that. So if L belongs, so let's say L is a set of language, and L bar is a sigma star. Sigma is all the 0, 1 string. L. Okay. So one can define also. So this is usually called co-L. Okay. Sorry, it's not the same. So for example, if we want to define co-NP, one just say that L belongs to sigma star, and the L bar belongs to NP. Okay. So so you can define any code language. Okay, for example, let's see. Okay, so one can define code L, defined to be L belongs to sigma star, and L bar belongs to the L. Okay, so simply speaking, just reverse all the for all. So just reverse for all to exist, and then exist to for all. Okay, so you just for a previous one, you just change this exist for all and change it for all to exist. So just simply do this, and you get another language. Okay, simple is very simple. So one can define. Let me just quickly define the polynomial hierarchy, and then I will prove some basic. I will just mention some basic fact, which is easy to prove, and then that's it. And then maybe in the future, I will talk more about more deep results. Okay. Definition. Okay, so pH. Okay, so one can define sigma p. Sigma p is this. Let's maybe let me just okay, so let me just do this kind of things. Will be easier. Okay, so remember what is NP. So NP is defined to be, let me just do a very sloppy, there exists, right? Certified, there exists some certificate, and then you get verifier. So let's call it exists P, means that there's the right hand side is some polynomial polynomial Turing machine, and the co-NP is like let me just write for all P. Okay, so sigma 2 is defined to be exist for all, so exist for all P, and pi 2 is you can define for all exist P. Okay, then you can just keep going, right? You can just define sigma 3 to be exist for all exist P. Okay, And then you will think why we don't use like for exist for all. Okay, the reason is that if you write exist, you can just combine to be a single exist. If you write for all, then you can combine this to be a single for all. Okay, so very stupid. And you can define pi3 to be for all sigma for all p. Okay. And just keep going. So let me just mathematically, I can write sigma I to be exist pi I minus 1. Hopefully you can see this. For example, sigma 3 is exist add on pi 2, so exist for all exist p. Okay, and the pi I is defined to be for all sigma I minus 1. Okay. Okay, and I define our polynomial hierarchy to be the union of sigma I. So I from 1 to infinity. Okay, so everything in all the sigma is defined to be is all this class combination union is called a polynomial hierarchy. Okay. And this is a fact that I will simply, let me just tell you that why it's true. It's actually the same as all the pi. Okay, and the reason is the following. Okay, so obviously that NP, obviously this NP, right? This NP is in both. Okay, let me just see this. Okay, so let me just say this. So obviously that your sigma I is exactly a subset of pi I minus 1. Why this is true? Because sigma I is because pi I plus 1 is defined to be for all sigma I. So if you just neglect for all, right? Let's say somebody can solve this pi I, you just neglect for all, then you can get the subset. You can get the sigma I. So basically, if you neglect for all, right? So you can neglect for all is the higher count, the largest is the powerful constraint, right? Let's say I can solve this problem for all for every, then I can solve the particular instance. So sigma I is a subset of pi I. Okay. So so obviously that if you is this true, right? So this is true. Okay. Okay. So also let me just write down. So this is a theorem which is trivial. If you just see a definition, this is a sigma modifier. So sigma I, for example, you can see that sigma 2 is exist for all p, sigma 3 is exists for all exists, right? So if you see this, there is, right, you can see sigma 2 is a subset of sigma 3 because it exists for all p and it exists for all c, exists p. So if you just replace this, if you just forget about one quantifier, then your problem should be weaker. Okay, so you get pi I subset of pi I plus 1, and the sigma I is a subset of pi I plus 1, and the pi I is a subset of sigma I plus 1. Okay, and our pH is so defined to be sigma I, so a union of pi I. Okay, so this, and so that means that if L belongs to pH, that means that L belongs to sigma I for some I. That means that this is it has a finite quantifier. Okay, that's it. And so one can draw a diagram, which is usually the computer science, so we go with PDR P to NP and the co-NP, and this is sigma 2. So when I use dot line, means that NP is a subset of sigma 2 and also a subset of pi 2. You do this. So do this. Okay, so this is the usual diagram in the polynomial hierarchy. And the Wikipedia just do the 900 degree rotation. Okay, so you can 90 degree rotation. I'm stupid. Okay, and obviously, so what is the higher class? What is the upper bound? Because this is only finite quantifier. If you allow to be infinite quantifier, which is T2PF, so obviously that polynomial hierarchy is a subset of P space. So since T2PF is a P space complete. Okay, so let me just write down some more detailed definition. So just make you happy. So now the detailed definition is this. So let's just write a detail down. So sigma p means that if x belongs L, there is this u1 belongs to 0, 1 to the length of q of x. And for all u2 belongs to 0, 1 q of x. And it is the u3 and up to let's say qi ui belongs to 0, 1 q to the x. And the m of x u1 u2 up to ui is 0 is 1. Okay. So qi is exist or for all by the even or odd. So for example, let's say sigma 2, you get exist exists for all. So that means that this is sigma. So that means by the even or odd. So if I is even, then you choose exist. If I is even, that you choose for all. So this is odd, and this is even. So is this odd and even? Okay, so this is a definition of this sigma I. So for example, sigma 2 is this and for all is what I just previous wrote. And one can define pi I if x belongs L. It means that for all u1, the same. It is the u2, for all u3, and the qi ui. Okay, m of x u1 u2 up to u some ui is 1. Okay, and also qi is for or exists by the even or odd. Okay, so this is the beautiful definition. This is very, very beautiful, right? Okay, so conjecture. Conjecture means that so every class in PH, so I should say every subclass in PH are different. So that means this P not so P do not the same as MP, and all the sigma I are different. Because you add more quantifier, it's amazing that even though you add this, no one can prove, right? Because people cannot prove that P do not the same as P space. So it's like every polynomial hierarchy. Oh, maybe it can be the same. But a conjecture says that sigma I are all different and pi are all different. So it means that every class, so every thing you see in this diagram are completely different classes. This is so amazing, like more powerful, like the powerful conjecture of the generalization of P do not same as MP. Okay, so theorem. Let me just recall some stupid theorem, which is very simple. Okay. Okay, so theorem 1 is that if P is the same as MP, then the P is the same as PH. So the proof is very simple because if P is the same as MP, right, you can call both sides. You can call P is call MP, which is call P is P, right? So which you prove MP is call MP. And obviously that if you write into language, which or the logic, which you prove that this is for all P, is this P, right? So this means that for all and exist looks the same, right? So once you add this, then let's say sigma 2 is this for all P. By definition, you can change it to is this P, which is P, right? Because I already proved that the P is the same as P, and also pi 3 is pi 2 is for all sigma P. You can replace for all to be exist, so is this P still P. Okay, so we proved that the sigma 2 and sigma pi 2 was also P, and then you can just keep going. Okay, so every sigma I is over P, pi I is over P for every I. Okay. Okay, so this is so that means all the PH will be P. All the PH will be P. Okay, so all the PH will be P. So the standard language is that the polynomial hierarchy collapse. Okay. And another theorem which is also important is that if sigma I is the same as pi I for some I. Okay, so for example, if P is equal if NP is equal to colon P, then the polynomial hierarchy collapse. So the PH is exactly the same as sigma I. Okay, so this terminology, let me just write down. This is important. So it's a hierarchy collapses to the i's level. Okay. So it's like everything in this kind of results. So everything in the complexity theory can boil down to if you believe that all the pH are different, and then you can try to prove that if your result is true, then maybe your results will lead to the collapse of polynomial hierarchy, let's say to second level or third level. So which may make people feel nervous, like this should not be true. Okay, so this is like the standard. This is a very fancy language, and you usually heard in the conference that people like to say the polynomial hierarchy collapse in the i's level means that sigma equals to pi I for some particular I. Okay. Yeah, and the proof is also simple. So it means that because if this is true, that means that you can change for all exist to the exist for all to the exist for all. So basically, this means that so you can change maybe for all exist is the same as exist for all Okay, if the list length is I. If both lengths are I, this means that you can replace this, and the next level you can use this as an identity, and you just keep going, and you can prove this. Maybe it's not easy to understand. Let me just simple example. Let's say NP is the same as colon P. It means that yeah, this is the same. I proved that for all exists. Okay, so if for all is the same as exist, then the sigma 2 is what? Sigma 2 is exist P, which is I can prove exist P, so it's NP. And also pi 2 is for all exist P, which I can also replace for all to be exist P, which is exist P, so it's also NP, which is for all P is the same as colon P. Okay, so you can see that the sigma 2 and pi 2 both belongs to NP and colon P. And then once you keep going, then you get sigma 3, pi 3 is also P or colon P. Okay, and I think this is almost what I like to say. What I like to say something. What I like to say. So let me just close this discussing the final topic called the natural complete problem. Natural complete problems. Okay. In PH. Okay. So remember what is the natural complete problem for natural complete problem for NP? It's like a set, right? So that means that you ask whether it is the x1 and x2 maybe up to xn for a formula or a circuit set to be such that this is true. And the colon P means that there for every this is called unset, which you want to ask whether this set is unsatisfiable. So for every x, x2, xn, such that phi of x1, xn is 1. You can say, oh, 0, right? But I can just reverse 0 and 1 and didn't change anything. Okay. So for sigma 2, the question is that there is this x1, let's say x. Let me just use a vector. Let me just use a vector. Let me just write down. So sigma I set, which is a language, is basically for all. It's like a phi of y1, y2 up to yn, and there exists z1 for z2. For all z2, and the phi of z1, zn is 1. z2. Okay, and all the zi and yi are Boolean vector. So it's like in a NP that you get the x vector such that the phi of x is 1, right? So for sigma I can just say that, oh, I want to ask where phi such that the phi z1, z1, z2, zn is 1, and but I replace each z1 to be a set of vectors. Z2 is a set of Boolean vectors. Okay, so yeah, just this. This is just this. Okay, and then you can also define a pi I set. just start from the same thing, but is it for all? Is it for all? Is it? Just it's exactly the same as the set. Just replace is this for all, is this for all, and add more. Okay, so it's very interesting class that you just someone like do the very simple generalization, but you get a whole class, which is very crazy. And most of the people can prove something is you can prove something if you assume that the polynomial hierarchy is never collapse. For example, if you can prove that graph isomorphism should not be NP complete, otherwise that polynomial hierarchy will collapse to second level. Or you heard about quantum computing, that you can prove that the boson, if boson sampling it can be solved in the polynomial there's a classical algorithm can solve efficiency, the polynomial hierarchy will collapse to third level. Okay. So this is the very interesting class called the polynomial hierarchy, and this is my introduction. Hope you guys love this.